everyone, this is my third conference presentation in the series, and this one takes us back now 2 years to the 2014 ARB conference, and this paper is titled, "Is Road Infrastructure That Improves Operating Speed a Double-Edged Sword When It Comes to Road Safety?" So what does the current literature tell us about new infrastructure? So if it's a new road, it's going to be safer than an old road. And that's simply because they install treatments such as, they could have better alignment, you've got wider shoulders, or you could have barriers and so on. And if it's upgraded from 2 lanes to 4 lanes, then you've got dual carriageways, which will reduce the chances of head-on collisions. Also as well, if there's congestion problems, you may have congestion-related crashes, which could involve potentially frustrated drivers and road rage. Also, start-stop, you're going to have rear-end accidents. And also new treatments in place can isolate particular accident types. So if there's one accident type that's very prominent, you can put in a treatment in place that deals with that particular accident, therefore making the road safer. What existing literature also tells us is that new infrastructure improves operating speed. Again, with the extra capacity on that, vehicles don't have to travel at 30-40 kilometers per hour, for example, if you're getting congested. You could go back up to the speed limits of maybe 100 and 110 kilometers per hour. Literature also tells us that more fatalities occur at higher speeds. And if you look at the literature, that is actually quite obvious. And if you look at the United States, reduction of speed limits has actually reduced fatal accidents by 16.4%. I think that was reduced from 70 miles per hour down to 50 miles per hour. Current literature was also generally focused more around the speed limits and how that affects safety rather than operating speed. And today's paper, we're going to be focusing a little bit more on operating speed than speed limits. So how are we going to establish a relationship between operating speed and safety? So what's been done is we've looked at particular sections of the Queensland network that offers us a range of speeds. And again, a lot of that is within southeast Queensland. So as you can see in the table here are the selected motorways and sections. Pacific Motorway all the way down to the border, got 79 kilometers there. Got the Bruce Highway, Brisbane to Maryborough, 225 kilometers. Sunshine Motorway, again about another 8.6 kilometers there. Gold Coast Highway, Helensvale to Coolangatta, 29.8 kilometers. Gateway Arterial Road, 11.3 kilometers. Warragul Highway, Ipswich to Toowoomba, about another 95 kilometers. And the Western Arterial Road, Ellen Grove to Jindalee. So this was data that we've collected over about 2 or 3 years in order to have a large enough data set to actually establish how operating speed and to establish a relationship between operating speed and fatal accidents. So operating speeds weren't actually available in the data. They had again the speed limits, they had the capacity of the road, how many lanes and all each section, and the traffic volumes, the daily traffic volumes. So in order to make a comparison between safety and operating speed, we had to calculate the operating speed based on the capacity of the road and the volume of traffic. So you can see here the graph. This is a relationship between volume capacity ratio and operating speed for motorways. This is 4 lane, 6 lane, 8 lane uses this graph here. So volume capacity ratio of below 0.4, we would assume vehicles are traveling at the speed limit of 100 kilometers per hour. Between 0.4 and 1, we would calculate the speed somewhere between 70 and 100 kilometers per hour. And then for a volume capacity ratio of between 1 and 1.25, we'd calculate the speed to be between 30 and 70 kilometers per hour. And then once we've got that average speed for each section, we'll then go and look at the number of accidents, how many fatal accidents, serious injury and property damage there is, and determine actually how safe those roads are for those particular speeds. So here are the results of the analysis that we conducted. So if we have a look at operating speeds below 70 kilometers per hour, we didn't actually collect any fatal accidents on those sections of roads, but more than half of the incidents actually were minor injuries, and we had about a quarter that were property damage. In fact, for that speed, that's the highest percentage out of all the speed categories we looked at for minor injuries. If we look at 70 to 80 kilometers per hour, I think we would have had a few fatalities. Again, less than 1% of accidents were actually fatal accidents, and numbers were quite similar to what we're getting for less than 70 kilometers per hour. If we go up to 80 to 90 kilometers per hour, we see there's a bit of a jump now, actually getting more than 1% fatal accidents. And we're seeing that there's also an increase in the number of hospitalizations, whereas minor injuries percentage-wise are actually a little bit lower. If we go from 90 kilometers per hour to 100 kilometers per hour, again, fatalities have gone up, now almost at 2%. Hospitalization, again, has gone up a little bit, and minor injuries are now down to just about 36% of all accidents. And once we get over 100 kilometers per hour, fatalities are actually up there almost at about 3.5%. Hospitalization has also increased. That's around, I think it was around 28 to 29%. And minor injuries have remained fairly constant, and property damage, again, it seems to be fairly constant across all the speed groups. But it seems like there's a clear inclination for more fatal accidents to occur once speeds seem to get over 90 and especially over 100 kilometers per hour. So how do our results compare to existing literature? So we got some data from Victoria and the numbers that they have. So again, we'll look at how our below 70 kilometers per hour compares to theirs. We had 0, they had 0.7, so it's quite similar on that. Hospitalization again is fairly similar, within about 1%. Other injuries and casualties, I think they've categorized them a little different. It's a little bit hard to compare. If we look at between 80 and 90, again is somewhat similar, and also they are experienced similar to what we're getting, with speeds above 100 and around the 110 kilometer mark. You're getting about 3 to 3.5% of accidents actually resulting in fatality. So again, they're experiencing that jump. So it seems like the work that we've done here in Queensland is actually producing very similar results using our methodology to what's been done in Victoria. So how do you put a value on safety? In transport, there seems to be basically two schools of thought. One is the human capital approach, and the other is the willingness to pay approach. Human capital approach basically looks at the cost of an injury or fatality in terms of income foregone, the cost it is to family in terms of disturbance of that nature, or you could be looking at in terms of hospital costs and what they are, costs and delays and also the transport network of having to close a road down temporarily, and along those lines, something that you can put a dollar value based on outcomes of certain events. The willingness to pay approach is a little bit more difficult, and there's a number of ways of going about that. You can use stated preference surveys. In a sense, you can be asking people, how much value do they put on their life, and that could be shown through a number of questions. Like, for example, would you take a more dangerous road that saves you 10 minutes compared to a road that's a lot safer? And you can, again, that you look at that in terms of what is their behavior, determine their approach to risk. So where the two differ in terms of values is we've got the willingness to pay approach, which came at a value of life, statistical value of life of about 7.5 million in 2013 prices, whereas you got the human capital approach, which is determined by Ostrows, which is considerably lower at around $2.6 million per human life. Again, the other types, hospitalization and minor injuries and stuff like that, the values came out to be quite similar. So it's really the loss of life being the biggest two between these two approaches. So we'll take a look at our speeds and all that, and what is the average cost based on the higher fatalities. So again, we've calculated it as an average based on the nature of accidents we showed previously. So using the human capital approach, the average cost is going to cost about $150,000. And if you're traveling at over 100 kilometers per hour, the average cost is going to be around $280,000. So it's almost double the amount. If we take a look at the willingness to pay approach, though, the cost of a crash below 70 kilometers per hour is under 100,000, so it's actually a little bit lower. But in terms of the cost of a crash above 100 kilometers per hour, because of the fatalities and because of the loss of life, that comes in at 362,000, which is almost 4 times the amount of the value of a crash that is under 70 kilometers per hour. If you look at it in terms of million vehicle kilometers traveled as well, you see actually because of the number of crashes below 70 kilometers per hour, the actual cost is higher at lower speeds because you've got a higher frequency of low speed crashes. Potentially, if there's any form of congestion, you get more crashes, but they're generally not very serious. So that's pushed it up. But if you look at it in terms of willingness to pay, again, it's that very high value of life that actually gives you a higher dollar value for a million vehicle kilometers traveled. So I'm now going to take a look at 3 different types of projects. Overtaking lanes, in a sense they add capacity and they also add safety. Highway duplication, so that is again going from 2 lanes to 4 lanes. Again, they're divided into dual carriageway, into 2 dual carriageways instead of the single one. And another one is a town bypass. Again, that's most likely going to be looking at a reasonably small local town bypass and how that may add safety or may not add safety. Okay, let's start with the overtaking lane. So what does an overtaking lane do? So if we start off with 2 lanes, you add the overtaking lane, that's going to give us 3 lanes, and that allows for safe overtaking. So now vehicles don't have to overtake into oncoming traffic. It should improve operating speed, because again, there's going to be more opportunities to overtake. So vehicles will be moving faster and they should be moving safer. So how do we actually calculate accidents with that? So a typical approach is we look at the actual section where the overtaking lane is. And Ostrows has produced numbers such as 25% reduction in accidents for the length of the overtaking lane. So an overtaking lane could be 1 kilometer, for example. That 1 kilometer should experience 25% reduction in accidents. We look at also what we got an upstream area. So that's the 3 kilometers prior to the overtaking lane. So what's been assumed here is that vehicles are not going to be less likely to risk dangerous overtaking if they know there's an overtaking lane ahead where they can overtake safely. So again, you get that added safety. Again, it's only a 2.5% reduction. And then after the overtaking lane, there's been an assumed 2.5% reduction for that 5 kilometers. That's assuming that vehicles have overtaken the slower vehicles and they don't need to overtake another vehicle for a while. So again, it's making the assumption that you've got a stretch of road where overtaking isn't required, therefore it's going to be safer. And it's only a 2.5% reduction. So a number of key assumptions had to be made. So we made the assumption that the average speed improves from 70 kilometers per hour to 100 kilometers per hour. The number of vehicles, the average annual daily traffic is 8,000. So we calculated it in our model, in our spreadsheet model, using the human capital values and also the willingness to pay values. So using the human capital approach, we came up with accident savings of about just over 1 million, and using the willingness to pay approach, we came up with accident savings of around 480,000. So again, both results indicate that overtaking lanes are actually improving safety, even though operating speed has increased, but simply because of those reductions in accident rate, because of the extra lane where where vehicles won't have to overtake into oncoming traffic. Again, the willingness to pay approach gives you less benefit simply because fatalities being so high and the higher speed potentially causing more fatalities than at the lower speed. But overall, the overtaking lane, even if you're going from 70 kilometers to 100 kilometers per hour, produces accident savings. The next project we looked at was a highway duplication. So we went from 2 lanes to 4 lanes. So what is this? Is an increase in capacity. And by going to a dual carriageway instead of the single carriageway, there will be a reduction in head-on collisions. And of course, because of the increase in capacity, we'll see improved operating speeds. So with the highway duplication, we made a number of assumptions. So we've assumed that the average annual daily traffic is 25,000 vehicles. Again, like with the overtaking lane, we've assumed that operating speed improves from 70 kilometers per hour to 100 kilometers per hour. So we've got a 2-lane average seal of 10 meters to a 4-lane dual carriageway. I had to state the seal width because, again, depending on the seal width, it has an impact on the accident rate. So this is a reasonably narrow seal compared to some of the wider 2-lane seals. We're using accident cost reduction based on the model road state, as mentioned. So the results indicate human capital approach. Again, we have some savings, just under $1 million worth of accident savings. Again, that kind of makes sense in the sense that head-on collisions and all that has been eliminated. Willingness to pay approach actually gives us negative savings, which is actually quite interesting. So it appears that even though we've got a reduction in crashes from reduced head-on collisions, potentially fatal, but because of the higher speeds, 100 kilometers per hour, there are actually still going to be more fatalities, and that high cost per fatality in the project case results in negative net accident cost savings. Next project that we considered is a town bypass. So the new road is bypassing an urban area, a small urban area. So what happens there is you're avoiding intersections within that urban area. So you're avoiding start-stop collisions and accidents, which normally intersections, they have a number of accidents. So again, though, normally there's not that many fatalities at intersections because of the lower speeds. So, and also now because we've got this bypass, again, you would expect to see quite an improvement in operating speed, in the sense that you don't have to go through a potentially congested urban area with intersections, etc. So for this town bypass, a number of assumptions were made. So we've assumed that 3 intersections are bypassed, that there's an annual average daily traffic of 20,000 vehicles using the existing road. After the bypass is built, we've assumed that 10,000 vehicles now bypass the existing roads. So we've now assumed, because we now got 2 roads, we've got the bypass and all that, the average operating speed again improves from 70 kilometers per hour to 100 kilometers per hour, consistent with our other projects. So what do we get? A human capital approach again produces accident savings of almost $1 million, but the willingness to pay approach again produces negative accident savings. Again, it's the same thing. It's the higher speeds that's producing those extra fatal accidents, even though the number of accidents are probably greatly reduced. But those relating to intersections and stuff like that generally don't tend to be fatal. But once a bypass has been built, moving at speeds of 100 kilometers per hour, based on our numbers that we showed earlier, is producing those high accident costs in the project case. So again, this project is actually, if we're using the willingness to pay approach, as actually causing a higher cost for accidents than if we hadn't gone ahead with the bypass. The approach adopted here for the examples is a little bit different than the typical approach that's used in cost-benefit analysis. Typically, we'd look at an accident rate for your base in your project case, and then we'd use an accident average cost across the board, which includes all the accident types. So here we've actually looked at accident costs per accident type. So we've got the fatal accidents, which is higher, etc. So again, that's a recommended use, that we actually focus more on the different types of accidents that we get at different speeds, rather than just using a flat average. What we've also found, that there seems what we're calling here the magic 90 kilometers per hour. It appears that once 90 kilometers per hour has been hit, it seems like roads become considerably more dangerous, in a sense that accidents above that speed are far more likely to be fatal, and that's consistent with what we've produced here, and also other literature, like in the US, we went from 70 miles per hour down to 50 miles per hour. Again, great reductions in fatalities. The Bruce Highway, it went down from, I think it was 100 down to 90 kilometers per hour. I think that was up to the Croy to Curra sections. Again, we noticed the same thing, a great reduction in the number of fatalities. Another approach is to actually use DCA codes, or road user movements. And again, that is a far more detailed look at accidents. You're actually breaking it down for a particular type of accident. Is this a head-on collision, again, which have a much higher cost because there's a much higher chance of fatality than if it's a rear-end accident, which almost never produces fatal accidents, but you could have injuries and property damage. Again, that will give us a more detailed perspective when we're trying to evaluate accidents for a cost-benefit analysis. So in conclusion, I'd just like to summarize the key findings of this paper. So we're looking at higher speed. So generally at a higher speed, you're more likely to have a fatal accident than if you're traveling at a much lower speed. But lower speeds that are caused through congestion tend to will give you a higher accident rate, and you'll get more accidents relating on start-stop and things like that. So lower speeds, more accidents, but at higher speeds you're going to have more fatal accidents and potentially far more costly accidents. And also as well, looking at the different types of projects, looking at overtaking lanes, which generally deal with both safety and improving capacity and improving operating speed, both from a human capital and also the willingness to pay approach, gives us positive accident savings, whereas some of the other projects that are very much focused on increasing capacity, such as bypasses and duplications, even though potentially they're designed to be safer and you're splitting between going from a single carriageway to a dual carriageway, but if these operating speeds are significantly faster, you're going to have more fatal accidents, even if the road is generally reducing the number of accidents. So again, that is something worth bearing in mind, and also as well in terms of designing some of these roads as well, in terms of you've got to cater for the chances of fatality. And also, again, it could imply as well, maybe you should have a speed limit of 90 kilometers per hour instead of 100 or 110 kilometers per hour, given what our research is indicating, that it seems like anything below 90 kilometers per hour, the number of fatalities are kept fairly low. So if you're improving the speed from maybe 60 or 50 kilometers per hour up to 90 kilometers per hour, the road chances are is going to be safer than it would be if you were to then increase the speed maybe to 100 and 110 kilometers per hour. I would like to thank you again to listening in another one of my conference presentations. Before I go, there's something I'd just like to leave you with. There was a safety campaign done by Transport and Main Roads, I think it was just a couple of years ago, and they would have these big flashing billboard signs and stuff like that, saying, you know, you shouldn't speed, you should do this, you should do that, safety first, and all that sort of stuff. But the irony was that you're actually having these boards at the side of the road, potentially causing a distraction of people looking for their own name on there that could actually cause more accidents. Again, that is rather ironic, isn't it, for a safety campaign that potentially could be causing danger, given the fact that it's being advertised on billboards along roads, which could be causing a distraction. Again, thank you.
If you like today's video presentation, just click the like button and the subscribe button, and I'll be uploading several more videos in the weeks to come. Again, within the same series, videos relating to the transport conferences, as well as several other videos also relating to economics. If you want to find out more about today's paper, just go to my website at spectrumecons.com and you go to the research paper, just click the link there and you'll get the paper in full. Again, thank you for listening. Goodbye.